In this video, we work more antiderivative problems using u-substitution. These are problems from section 5.2, which is about antidifferentiation and integration with the logarithmic function. So almost all of these antiderivative problems that we'll be working are related to this antiderivative. The antiderivative of 1 over x with respect to x is natural log of the absolute value of x plus c. So if this is a u rather than an x, we'll have natural log of the absolute value of u plus c. And so if that integral can be written in that form, or can it be written in the form of something that we know the antiderivative of plus a 1 over u or a constant over u term, then we should be able to compute that antiderivative. So I've got an integral like this. And every time we see an integral, we're going to ask ourselves, do I have a basic rule for that? And we don't. We don't have any quotient rules for antiderivative. And what we have here is a rational function. We've got a polynomial divided by a polynomial. So we say, okay, well, what techniques do we know? Well, other than our basic rules, we know u-substitution. If the function here can be written entirely in terms of u, and du, that's the derivative of u times dx, is a factor up here in the integrand, then we might be able to write the integral in terms of u. So in this case, when you're looking for u-substitution, usually you're looking for a function nested inside another function. So you're usually looking for parentheses. Some expression inside the parentheses might be our u. You're looking for a function maybe inside a trig function or inside the exponent of an exponential function, under a radical or something like that. In this case, what we see is, well, we don't have any parentheses. So our best guess based on the form of this integrand is that u is the denominator. So we'll let u equal the denominator. And then we'll compute du. Du is the derivative of this times dx. So we're going to have 3x squared plus the derivative of 3x squared, which is 3 times the derivative of x squared, which is 2x, plus the derivative of a constant times x, which is that constant. All that's multiplied by dx. And we're comparing this to the integrand. We're saying, do I have du or a multiple of du as part of my integrand? And I do. If I factor out a 3 from this, this is 3 times x squared plus 2x plus 3 times dx. I have an x squared plus 2x plus 3 times dx in my numerator. So don't need this extra factor of 3, so I can divide both sides by 3. 1/3 du is x squared plus 2x plus 3, that quantity times dx. So this integral can be rewritten entirely in terms of u in the following way. We'll have 1 divided by this x cubed plus 3x squared plus 9x times the x squared plus 2x plus 3 dx. And this is 1 over u by design because that's what we've chosen u to be. And this x squared plus 2x plus 3, that quantity times dx, is actually 1/3 of du. So we can substitute that in. And then we say, do I have a basic rule for that? And I do, it's that rule. And we just have a u instead of an x. So I have a 1/3, I'll bring that out front, times the antiderivative of 1 over u with respect to u. So we'll get 1/3 of the natural log of the absolute value of u plus c. And then we want our final answer in terms of x, not u. So we replace u with whatever it was in terms of x. And u was that x cubed plus 3x squared plus 9x. So we'll substitute that in. And that is our antiderivative. Now we don't have to, but if we want to, we could check our answer by differentiating this. And if you take the derivative of this, you should get that integrand back after simplification. So let's check by differentiating. We have the derivative with respect to x of 1/3 natural log of the absolute value of that x cubed plus 3x squared plus 9x plus c. And we get 1/3 times 1 divided by the inside function, because the derivative of natural log of a function is 1 over that function. And when you have the absolute value bars around it, you can just ignore those absolute value bars because of the because of the things that we've already talked about. So you have 1 divided by the inside function times the derivative of the inside by the chain rule. And that's 3x squared plus 9x, or plus 6x, excuse me, plus 9. And then we add the derivative of c, which is 0. And then each of these coefficients can be divided by 3. So we end up with an x squared plus 2x plus 3, all divided by x cubed plus 3x squared plus 9x. And that is our original integrand, so we know we did the antidifferentiation correctly. We can just divide each of these by 3 and then think of that as itself over 1, multiply straight across, and we get that. All right, so that's one example. Let's look at another example. Here we have x cubed minus 3x squared plus 5, all divided by x minus 3. Excuse me. Ooh, wow. So we have that. Now there are a couple of ways we could handle this. We could do long division first because we've got a degree 3 polynomial divided by a degree 1 or a linear polynomial. So we might get something quadratic plus a remainder over our divisor. And that remainder over the divisor we could, or did I say that? Yeah, remainder over the divisor. The remainder of the divisor will have the degree 0 polynomial or a constant divided by x minus 3. And we can handle that with a u-substitution. So we might do that. Or we could actually recognize these two terms have an x squared in common. This is x squared times x gives me that first term, and x squared times -3 gives me the second one. So now if I want to, I can take this expression and divide by x minus 3. And then add 5 divided by x minus 3. And the x minus 3 is reduced, and you just end up with an x squared. That's nice. That's the same answer that we would get if we use long division. But we see in this case, long division was not necessary because we recognize that we could divide out that x minus 3 because we could factor out that x squared. So this is just using the property that if you have a plus b divided by c, that's the same as a divided by c plus b divided by c. Usually we go from right to left, but sometimes with these problems, we tend to go from left to right. If we have the same denominator, you just add the numerators and keep the common denominator. Or if you've got one fraction and you've got a number of terms in that numerator, you can split it up. You can take that first term in the numerator and divide by the x minus 3, and then add the second term in the numerator divided by the x minus 3. But for this, it's relatively simple. This is a basic rule, and this one requires a very simple u-substitution. So we'll have the integral of x squared with respect to x plus, I'll factor out that 5 times 1 over x minus 3. The integral of that function with respect to x. This one is just a power rule. So add 1 to the exponent and divide by the new exponent. And then for this one, bring the 5 down, and we'll have u-substitution. We'll use a u-substitution. So what is our u? Well, u should be that x minus 3. And then we'll have a 1 over u there. And du is the derivative of u with respect to x times dx. Well, the derivative of x minus 3 is just 1. So du and dx happen to be the same thing. So in that case, when we rewrite the integral entirely in terms of u, we get 1 divided by u times du. Then we say, do I have a basic rule for that? And we certainly do. That's going to be natural log of the absolute value of u plus c. And then finally, we back substitute u is x minus 3. That's our antiderivative. So this time, we did use a u-substitution to evaluate an integral of the form 1 over u du. But we had to do some algebra first. We saw this polynomial divided by a polynomial, and we decided to divide. We could have used long division if we wanted to. We could have also used synthetic division if we wanted to. But instead, we said, hey, if I factor out an x squared from those first two terms, I have an x minus 3 as a factor of that. And I'd like to cancel the x minus 3. So then because of the form of this particular integrand, we could avoid long division, we could avoid synthetic division and get to this answer. If you use long division or synthetic division to divide, we would have obtained this answer anyway. So then we use a basic rule and a u-sub there. So let's see, what did we do? We rewrote the integrand. And you want to do that so that basic rules apply. There are basic rules and or u-sub apply. Because u-substitution is our most advanced technique. And then we evaluate each of those integrals separately. Or we can call them antiderivatives. And then for the u-substitution, you choose u. You compute du, write the integral in terms of u. Anti-differentiate in terms of u. And then back substitute, u is x minus 3. All right. We can differentiate that. And we should get the same answers as we have right there. I think it's easy to see that the derivative of 1/3 times x cubed is 1/3 times 3x squared. The 3 and the 1/3 cancel and we get an x squared there. So that's that. And the derivative of this is 5 times 1 over x minus 3 times a 1. So that's a 5 divided by x minus 3. So we can see that those are equal to each other. Now, if we multiply this expression, this x squared by x minus 3 over x minus 3 and distribute, then we get the original. And we would, after distribution and then saying, well, we've got the same denominator, so we add the numerators and keep the common denominator, we would get back to this. So we sort of just did the checking that by taking the derivative of the antiderivative in our heads, and we could see that the derivative of this is this, which simplifies to this, which simplifies to that. So our antiderivative is correct. Okay, so let's do another one. I've got an x to the 4th plus x minus 4, all divided by x squared plus 2. Say, do I have a rule for that? No. But I've got a degree 4 polynomial divided by a degree 2 polynomial. I might be able to use long division to rewrite it. So this is what we do. When you use long division, that polynomial in the numerator has to include all of the powers of x, starting with that highest power of x. So we're going to add some placeholders. We've got an x to the 4th, and then we'll add a 0x cubed, because there are no x cubed terms. And then we need our x squared term, so we're going to add a 0x squared. And then we need our x term, which is that plus x, and then our constant term, which is a minus 4. And all of that is divided by x squared plus 2. You don't have to have a placeholder here, but some people choose to and say, well, I need an x term, so that would be a 0x and then a plus 2. Now we'll do the long division for this. I think I'm going to leave that 0x out of my x squared plus 2. But I'll leave the placeholders in for the x cubed and the x squared terms in that numerator. So now if I want to divide this by this, I just write this under the sort of division box. I don't remember what that's called. And then this is our divisor. This is called the dividend, and this is the divisor. And we just ask ourselves, well, x squared times what will give us this x to the 4th? X squared times x squared gives us x to the 4th. So I place that x squared above the x squared term here. And then I distribute that x squared to all of this here. It's just like doing this long division problem. I say, how many times does 13 go into 2? It doesn't. How many times does 13 go into 27? It goes in 2 times. Then we multiply, we get 26, we subtract, we get 1, we bring the 8 down, and then we try it again. But instead of saying how many times does 13 go into 27, now we're going to say how many times does x squared go into x to the 4th? Or alternatively, x squared times what will give me an x to the 4th? Just looking at those first 2 terms, and we say x squared times x squared will work. Then, like we do here, we put the x squared up there, we put the 2 there, then we multiply those 2 together and put that product down here. Now we're going to multiply this x squared by this x squared plus 2. We'll get x to the x squared times x squared. You add the exponents, that's x to the 4th, plus 2 times x squared, that goes here. And then we subtract here. So we're going to subtract here. Then these reduce. We end up with a negative 2x squared there. Then we can bring down that plus x and that minus 4. And then we focus on that leading term. We say x squared times what will give us this negative 2x squared. I just need a negative 2. So then we do negative 2 times that entire quantity. Negative 2 times x squared is negative 2x squared. Negative 2 times a positive 2 is negative 4. And we subtract. So we're going to change the signs and add like terms in columns. Those are going to reduce. Then we have an x there, and then those reduce. And then we stop here because the degree of this polynomial is less than the degree of that polynomial. This expression is called the quotient. This is the remainder. And this expression that we're dividing by is called the divisor. So what we get when we are finished dividing is the quotient, which is x squared minus 2, plus the remainder divided by the divisor. So we have plus an x divided by x squared plus 2. And this just requires some basic rules, and that we can do with u-substitution. Okay, so the antiderivative of this piece can be found using basic rules. So we add 1 to the exponent and divide by the new exponent. The antiderivative of a constant with respect to x is just that constant times x. And this requires u-substitution. So I'm just going to rewrite that integral. Now, again, whenever we do u-substitution, first we say, do I have a basic rule for that? And then we say no. Okay, if we don't have a basic rule, then we use u-substitution. Then when we do use u-substitution, we're looking for a function nested inside another function. So looking for a function inside an exponential, inside a trig function, under a radical, or something like that. If there are no parentheses to indicate an inside function, and there are no exponents, trig functions, radicals, usually in that case, u might be the denominator if you've got a quotient involving functions of x. So we'll try u equals x squared plus 2. And if we have a multiple of the derivative of x squared plus 2 as part of our integrand, we'll be able to evaluate this antiderivative. So we'll let u equal x squared plus 2. Then du is the derivative of this, which is 2x times dx. And we compare this 2x dx to what we have up there. We say, do we have a 2x dx? We say, almost, we've got an x dx. So that's great. We can just get rid of that 2. And then if we got rid of that 2, then we'd have an x dx. We can get rid of that. We can solve this equation for x dx if we multiply both sides by 1/2. So we have 1/2 du is x dx. So this is a u in the denominator. This expression is 1/2 of du. So we end up with 1 over u times 1/2 du, and that 1/2 we can bring out front. So we're almost done. We've got that 1/3 x cubed minus 2x plus the integral of 1 divided by u times the 1/2 du. The 1/2 goes out front and the du goes on the far right. And we say, do I have a rule for that? And we do. The antiderivative of 1 over u is natural log of the absolute value of u plus c. And then we want a final answer in terms of x. So we back substitute. U is this x squared plus 2. So we're going to substitute that in. And the absolute value of x squared plus 2 is x squared plus 2 because x squared plus 2 is already greater than or equal to 2. It's never negative. So we don't really need the absolute value bars in that case. You can keep them there. They're just redundant. They don't tell you anything new. So that is my final answer. Whoops. And if we differentiate that and simplify, I think we're going to get this. And then if we get a common denominator here, by multiplying this expression by x squared minus 2 divided by x squared plus 2, I believe we get this denominator, or this original integrand. So I'm not going to check this one. But we could, by differentiating, obtaining that answer, and then getting a common denominator to obtain that integrand. All right. Now let's look at another problem. Let's say you have the antiderivative of natural log of x quantity cubed divided by x. Okay. Say, all right, do I have a basic rule for that? No, we don't have a basic rule for any quotient, not when it comes to antiderivatives. So we have to use our most advanced rule, which is u-substitution. So you're looking for a function nested inside another function. You say, well, that natural log of x is in that x cubed function, or that cubic function. So this must be our u. We're never sure that will work until we actually write that down. U equals natural log of this x, and then compute du. You say, what's the derivative of natural log of x? It's 1 over x, then we multiply by dx. And then we say, can I rewrite that entirely in terms of u? I sure can. Is there a factor of 1 over x dx? And you say, yes. Now, some students find that misleading. They say, I see an x dx, but I don't see a 1 over x dx. Well, that actually is a 1 over x dx because that x is in the denominator. So I can rewrite this integrand as natural log of x cubed times 1 over x dx. And you can think of this as itself over 1. If you multiply straight across, you get the original integrand. So we know that'll work. Now we want to write everything in terms of u. So I've got natural log of x cubed is actually u cubed. 1 over x dx turns out to be du. And then we say, do I have a basic rule for that? And we do. So we add 1 to the exponent. And then we divide by the new exponent. Don't forget to add c. And then we replace u with whatever it was in terms of x. It was natural log of x. So we substitute that in. And that is our answer. Now, if we differentiate this using the chain rule, we'll have 1/4 times 4 is a 1 times a natural log of x to the 1 less power. So we'll have natural log of x cubed times the derivative of the inside, which is 1 over x. So that gives us here. And then if we write that as itself over 1 and multiply straight across, we get the original integrand. So this is the antiderivative of that, because if we take the derivative of it, we get the integrand back. Here's another one. Okay, so we're looking at that. We say, do I have a rule from that? And we say no, because we have the sum of terms involving x values raised to rational exponents. So we don't have a basic rule for that. It would be fine if they were in the numerator. We could just distribute and use the power rule. But since they're in the denominator, we don't have any way to simplify it. So I'd say, okay, well then I need to use u-substitution. I'm looking for a function nested inside another function. Usually one of the indicators of what that function should be is a set of parentheses. So since I see that 1 plus x to the 1/3 in parentheses, I'm thinking that's probably my u, but we aren't really sure until we compute the derivative. So let's let u equal 1 plus x to the 1/3, and then we compute du. Well, the du is the derivative of 1, which is 0, plus the derivative of x to the 1/3, which we can find using the power rule. So that's 1/3 times x to the 1 less power. 1/3 minus 1 is 1/3 minus 3/3. 1/3 minus 3/3 is 1 minus 3, which is -2 divided by 3. So -2/3. That's the derivative of u times dx is our du. And then we might rewrite this. X to a negative power is 1 over x to the same power but positive. And we say, do I have a factor of 1/3 times 1 over x to the 2/3 times dx? Say I don't have the 1/3, but I do have the 1 divided by x to the 2/3 times dx. So we can get rid of this 1/3 factor. We get solving for this expression by multiplying both sides of this equation by 3. So we'll have 3 du equals 1 divided by x to the 2/3 power times dx. So this times this is 3 du. And I'll write my 3 on the far right, or excuse me, on the far left, and I'll write my du on the far right. And then I have my u in the denominator, but there's still an implied 1 in that numerator. And you say, do I have a rule for that? We certainly do. So the antiderivative of 3 times 1 over u is 3 times the natural log of the absolute value of u plus c. And u is that x plus, or 1 plus x to the 1/3. So we back substitute, replacing u with 1 plus x to the 1/3. And that is our antiderivative. If we differentiate that and we simplify, we'll get that. So we'll have 3 times 1 divided by that function times the derivative of the inside, which is that. That 3 and that 1/3 will cancel, and you'll end up with the 1 divided by x to the 2/3 times that quantity 1 plus x to the 1/3. This one's kind of fun. We've got an x times x minus 2 divided by x minus 1 cubed. Okay, there are a lot of parentheses there. So do I have a rule for that? No, not yet. But could I possibly write this all in terms of a new variable u, and where I would have a rule for that? And say, well, maybe. So here I'm looking for a function nested inside another function, and we see a couple of possibilities. We might let u equal x minus 2, and then take the derivative of that. Or we could let u equal this x minus 1. I would recommend using the x minus 1 because it's in the denominator. And you'll see why that benefits us in just a moment. So if u is equal to x minus 1, well, then we can compute du. Du is the derivative of this, which is 1 times dx. So now when I rewrite my integrand, that denominator becomes a u cubed. And the dx and du are the same thing. But we say, what am I going to do with that x? And what am I going to do with the x minus 2? Well, I can rewrite the x and the x minus 2 in terms of u using this equation. I can solve this equation for x by adding 1 to both sides. So x is equal to u plus 1. So I can replace this x with u plus 1. And that's fine, as long as I also replace this x minus 2 with a function of u. Well, if x is equal to u plus 1, x minus 2 is u plus 1 minus 2, which can be simplified as u minus 1. So x minus 2 is u minus 1. So I'm replacing that x minus 2 with u minus 1. So we are literally replacing all of these functions of x with functions of u, and we replace that denominator with that u cubed. And then the dx was du, and we say, do I have a rule for that? You say, not yet, but because I let u equal that x minus 1 in the parentheses, we just have one term in the denominator now. It's just a u cubed. So if we distribute in the numerator and then divide every term by u cubed, we should be able to use a power rule to compute the antiderivative of this in terms of u. So let's distribute in the numerator. First times first is going to give us a u squared. Outer times outer is negative u. Inner times inner is positive u. So those reduce. Last times last is negative 1. And then we're dividing all of that by u cubed. So now we can divide term by u cubed. And then simplify. I get u squared over u cubed minus 1 divided by u cubed. We're anti-differentiating with respect to u. 2 of those u's reduce there, and we just end up with a 1 over u factor. So that'll be a natural log when we anti-differentiate. And this, we don't have a rule for, but we can bring that up to the numerator. Because we know that 1 divided by x to a positive power is x to the same power but negative. This is just u to the negative 3rd power. So we end up with this. We say, do I have a rule for that? Yes, it's natural log of the absolute value of u. And then for this one, we bring the -1 down. And then we say, what is the antiderivative of u to the -3rd? We add 1 to the exponent. -3 plus 1 is -2. And then we divide by the new exponent. Dividing by a -2 is the same as multiplying by -1/2. Negative times a negative is going to be a positive, so we get a +1/2 there. Then we add c. And u was x minus 1. So this is going to be natural log of the absolute value of x minus 1 when I back substitute. And then this expression is 1/2 times 1 divided by u squared. And u was x minus 1. So you substitute that in. Don't forget to add your c. And so we get natural log of the absolute value of x minus 1. And if we multiply straight across here, we have 1 divided by 2 times the quantity x minus 1 squared plus c. And that is our antiderivative. I've heard this called fancy factoring. I don't really think of it as fancy factoring. I just think of it as rewriting this integral in terms of u and then saying, okay, I don't have a basic rule for that, but what can I do so that I do have a basic rule for that? Distributing and then dividing everything, separating that numerator into a number of terms and then dividing each term by that denominator. That gets us to a point where we can use our basic rule, so we do. Now, if we had chosen u equals x minus 2, we could have rewritten everything in terms of x minus 2. Then we would have had a u minus 1, or well, u plus 1 actually, cubed in the denominator. But u plus 1 cubed in the denominator actually wouldn't help us. We wouldn't be able to simplify it because we wouldn't have just one, well, we would have that one term in the denominator, but we wouldn't be able to use the u substitution to finish the problem. So allowing u to be that expression that was cubed allowed us to rewrite that integrand in such a way that our basic rules applied. All right. So that is our antiderivative. Let's get a couple more. And then we'll probably do something else in a different video. So this one's a little tricky. You've got 1 divided by the quantity 1 plus the square root of 2x. You say, do I have a rule for that? No, I don't. But I might be able to rewrite this using a u substitution. Now, because of the square root, you might be tempted to say that u equals 2x. But I don't think that would get us to a place where we could anti-differentiate. Because the derivative of 2x is just a 2. So we'd have a 2 dx as our du. And then we'd have 1 divided by 1 plus the square root of u. And we don't have a rule for that either. Since we don't have a rule for that either, it might be helpful to let u equal this square root of 2x, or let u equal 1 plus the square root of 2x. Let's see if that works. I want to include the 1 because that will simplify the denominator as much as possible. If I include the 1, then the entire denominator is my u. So let's let u equal 1 plus the square root of 2x, which can be written 1 plus the quantity 2x to the 1/2 power. Then du can be found using the derivative of a sum and then the chain rule for this piece. The derivative of 1 is 0. The derivative of a function to the 1/2 is 1/2 of the function to the -1/2 power. And we put the inside function back inside. And then we multiply by the derivative of the inside by the chain rule. So that's our derivative. Then we multiply by dx. The 1/2 and the 2 reduce. And so that ends up being a 2x to the -1/2 power, or 1 divided by the square root of 2x times dx. So you say, okay, that's a little bit frustrating because I've got du in terms of x, but I don't have a factor of 1 over the square root of 2x. But I can get the square root of 2x in terms of u because I have this equation. I know that the square root of 2x is, the square root of 2x plus 1 is equal to u. So if I want to, I could solve for the square root of 2x by subtracting 1 from both sides. The square root of 2x is actually u minus 1. So this can be written as 1 divided by u minus 1 times dx. And you might say, well, that still doesn't help me. Well, if I solve for dx, that gives me that dx is equal to, or if I want to solve for dx, I'll multiply both sides by u minus 1. Then I'll have u minus 1 times du equals dx. So this dx can be replaced by a function of u. And that's what we want. We want to write everything in terms of u instead of writing everything in terms of x. So, okay, now we want to substitute. We say we've got a 1 in the numerator. This 1 plus the square root of 2x, that was our choice for u. So that's replaced with a u. And dx is u minus 1 times du. And we can write that as itself over 1. You can multiply straight across. And then we'll end up with a u minus 1 divided by u times du. Now, since we only have one term in the denominator, we can divide each of those terms by u. U divided by u is 1. And then we're subtracting 1 divided by u. Say, do I have a rule for that? I do now. The antiderivative of 1 with respect to u is u. The antiderivative of 1 over u with respect to u is natural log of the absolute value of u, and then we add c. Then we say, well, what was u? Well, u is 1 plus the square root of 2x. So we replace u with 1 plus the square root of 2x here. And then we have the negative natural log of 1 plus the square root of 2x there. Then we add c. And so that is our antiderivative. Okay, well, what did we do again? It was a little tricky. But first, we looked for an inside function. We could have let u equal 2x. We could have let u equal the square root of 2x, or we could have let u equal 1. But the whole goal is to write that integrand in a form that will allow us to compute the antiderivative. So I said, if I've got something that looks like a potential u plus a constant, I always include that constant, because when I take the derivative of the constant, I'll get 0. And so that including that in my u will simplify things usually. So I said, let's try this and see if it works. I'm never really sure if it's going to work until I actually compute the derivative. So I said, let's let u equal this. So we choose our u. Then we compute du by taking the derivative and then multiplying by dx. And then I wanted to get, after I computed that du, I saw this expression and I said, I've got a function of x times dx, and that function of x is not up here as a factor. Usually I would say, it's probably not my u-sub, I should quit. I said, but I really need to do something. This time I was actually able to get this function of x in terms of u by solving this equation that told me that u was equal to 1 plus the square root of 2x. That allows me to get the square root of 2x in terms of u by solving for that expression in that equation. So we're able to do that. We write this expression in terms of u, and then because that's in terms of u, we can write dx in terms of u. So we compute du. In this case, we write dx in terms of u. That's not always necessary, but we're comparing what we have in the integrand to what we have here for our du. And if we don't have that exact extra factor, we might need to modify it in some way, either by writing it in terms of u or, well, actually, it's usually just writing it in terms of u that gets us up here. But I was thinking, really, what do I have? I have a 1 dx. So I need to get 1 dx in terms of u. So I need to write this in terms of u and then multiply both sides by it to get dx by itself. And then we just substitute. So you're going to write everything in that integral in terms of u. The dx needs to be written in terms of u. The integrand needs to be written in terms of u. And then we simplify that, and we say, do I have a rule for that? Not yet, but if I divide term by u, I get something that I do have a rule for. So then we do the rewrite so that our basic rules apply. Then we compute the antiderivative or antidifferentiate. And finally, we back substitute. All right, that's that. Now I've got the antiderivative of x to the 1/3 divided by x to the 1/3 minus 1. This is going to be very similar to what we did before on the last problem. I'm looking for an inside function. You might think x to the 1/3 is it because you've got that in the numerator and denominator. But because I have that minus 1, I think I want to include that in my u because I'd like to take whatever this says up here and divide it by just a single term, just a u. So I'm going to let u equal that x to the 1/3 minus 1. And then we compute du. So we have 1/3 of x to the 1 less power. 1/3 minus 1 is negative 2/3. Then we multiply by dx. So that's going to be 1/3 times 1 divided by x to the 2/3 dx. Say, do I have anything that looks like that here? So no, not really. Well, I can get x to the 1/3 in terms of u by adding 1 to both sides. But x to the 2/3 would require squaring that. So, I mean, we could get this dx in terms of u, but it's kind of a pain. So I think we might have to do that though. So I've got u in the denominator. I need something to take care of that x to the 1/3 in the numerator. Well, I could replace that x to the 1/3 with u plus 1 if I wanted to. Say, okay. But then this dx needs to be written in terms of u. So that means we need this x to the 2/3 in terms of u. So I'm going to multiply both sides of this equation by 3 times x to the 2/3. I'm trying to get this entirely in terms of u. And we say, well, x to the 2/3 is actually x to the 1/3 squared because of that exponent property. If you raise x to a power and then raise it to a power, you just multiply the exponents. So that x to the 2/3 is this x to the 1/3 squared by that exponent property, and x to the 1/3 is a u plus 1. So dx is actually 3 times u plus 1 quantity squared times du. So dx can be replaced with this function of u. You might say, is that simpler? No, but hopefully we'll still be able to evaluate the antiderivative. Okay, so now let's look at the integrand. You're going to rewrite every piece, every term in this expression needs to be written in terms of u. Say, okay, what am I going to do with that x to the 1/3 in the numerator? Well, x to the 1/3 is u plus 1. So we're going to replace that x to the 1/3 in the numerator with a u plus 1. And then the dx, what are we going to replace that with? It's this expression. It's relatively involved. It's 3 times u plus 1 squared times du. That's my new dx. Or that's what we're replacing dx with. That's what dx is in terms of u. And this denominator was a u. We have some implied parentheses there. Now, if I write this as a fraction, multiply the numerators, multiply the denominators. And what we have is 3 times u plus 1 squared times an extra u plus 1. That's going to be 3 times u plus 1 cubed divided by u times du. We say, do I have a rule for that? No. But I can write u plus 1 times u plus 1 times u plus 1, and I can distribute and evaluate that expression. And then I can divide each term in that expression by a u, and I should just be able to use the power rule. So it should be relatively straightforward. We can use Pascal's triangle if we want to find the coefficients of u plus 1 squared. We start with a 1 and then 2 1s here, and then a 1. You always have 1s on the ends. And then you add these 2 numbers together to get this middle number. Add these 2 numbers together to get a number. Add these 2 numbers together to get a number. Now these are the coefficients of this binomial expression raised to the n. So if we had a plus b squared, that turns out to be a squared plus 2ab plus b squared. Notice that the coefficients are 1, 2, and 1. Those are given by Pascal's triangle. So for a plus b cubed, our coefficients are going to be 1, 3, 3, and 1. And then the way it works with the a's and the b's, you start with a cubed, and then the powers decrease. So you're going to have an a cubed plus 3a squared plus 3a, and then our last term is a to the 0, which is just a 1. And then over here, you're going to start with b cubed, and then a b squared, and then b to the first, and then b to the 0, which is just a 1. So this is a plus b quantity cubed. Here, instead of an a, we've got a u, and our b is just a 1. So this turns out to be 3 times u cubed plus 3u squared plus 3u plus 1. And we're taking each of those terms and dividing by u. And you can factor that 3 outside of our integrand. So you end up with 3 times u cubed divided by u, which is u squared. And then one of those u's will reduce, so we've got a 3u there. Then the 3u divided by u is just the 3. And then the 1 over u is going to give us a natural log when we take the antiderivative. So that's our new integrand. Now we can apply our basic rules. So you have 3 times. Let's use the power rule. Add 1 to the exponent, divide by the new exponent. Then we bring the 3 down. This is a u to the first. Add 1 to the exponent and divide by the new exponent. The antiderivative of a constant is that constant times our variable. And the antiderivative of 1 over u is natural log of the absolute value of u plus c. So that is our integrand. And then we got another problem there from a different video. If we distribute the 3, we get 3 times 1 over 3, which is 1, times u cubed, plus 3 times 2/3 is 9/2 u squared. 3 times 3u is 9u. And then we've got 3 times the natural log of the absolute value of u plus c. And then we replace u with whatever it was in terms of x. Well, u is this x to the 1/3 minus 1. So we're going to have x to the 1/3 minus 1 cubed plus 9/2 times x to the 1/3 minus 1 squared plus 9 times x to the 1/3 minus 1 plus 3 times the natural log of the absolute value of x to the 1/3 of minus 1 plus c. And that is our antiderivative. All right. So we just did a bunch of u-substitution problems. And some of them required a little bit of algebraic manipulation to get that integrand into a form involving u. And then we might have to use even more algebra to write that in a form that I can apply our basic rules to. So we did that, and we were able to apply our basic rules. And so we were able to finish the problem from there. That's a different problem there at the top, sorry. I'm in an environment that's a little bit loud, sorry about that. So that is our antiderivative, and then we plug in the functions for u, and we get our final answer. Now, if we wanted to, we could differentiate this and try to simplify. And then hopefully after a lot of simplification, we would get this. But it would take probably a very long time to take the derivative of this, simplify, and then show that that derivative is equal to that. But I believe it can be done. The reason why it would look so complicated is because in order to get this function in a form that we could apply our basic rules to, we had to rewrite this as this expression involving u, which is relatively involved. So that's why it looks as bad as it does. But provided all of our algebra is correct, and I think it's correct, provided our u-substitution is correct, and I think it's correct, I believe this is the antiderivative. You can always check it and see by taking the derivative and simplifying. But that's our last one. Well, last one involving x. Let's do one involving trig functions, and then we'll go. This one's super simple. So we've got this problem, and we say, do I have a basic rule for that? No. Say, okay, well then what can I do? Well, probably u-substitution. Now we know that u-substitution will work, or we suspect u-substitution will work if we see a composite function, and we know that u-substitution will work if after choosing u, we see a multiple of du as part of our integrand. So I'm going to let u be this denominator. Then we compute du. The derivative of secant of x is secant of x times tangent of x dx. And then we say, is that a part of our integrand? Do I have that as a factor of my integrand? And I do. I've got a secant of x dx right there. So this becomes a 1 over u, so I've got my u in the denominator, and secant of x dx, secant of x tangent of x dx is the same as du. So we just end up with a 1 over u du. The antiderivative of 1 over u is the natural log of the absolute value of u plus c. And then u is actually secant of x minus 1. This is just a problem from the book. All right. So if I take the derivative of this, we get 1 over the inside function times the derivative of the inside. We get that. That's our integrand. So this is the antiderivative of that function. All right. I think we're done with those antiderivatives. In the next video or two, we'll probably do some definite integrals, which will involve u-substitution and then substituting the bounds as well. And I think that'll be it for all of the integrals involving logarithmic functions. This is from section 5.2 of that calculus, Larson calculus book. It's sort of late transcendental, so all the transcendental functions are focused. We focus on the transcendental functions, excuse me, in chapter 5. So this section was supposed to be about integration and antidifferentiation involving natural log functions. That's why we see so many 1 over u du's in our integrands. So, okay, done with that. We'll see you next time for some definite integrals.